each phototube, there's sort of a cone that both collects light that's coming from the mirror and bounces it into the phototube, but also it blocks light that is coming from larger angles. So the field of view of the phototubes is restricted, so that they really only see light that's coming off the dish of the mirror, and light that's coming from larger angles is blocked off.
How about starlight?
But even so, right, there's the starlight in the night sky, that light is hitting the phototubes, and the phototubes are actually seeing background skylight at the rate of about 100 megahertz. So on average, about every 10 nanoseconds, there's a photon that's recorded by the TMTs. So these are in a very bright environment compared to looking at the scintillation light that you have, and the tubes are on a lower gain to accommodate this. So they have the same sensitivity. They're still sensitive to single photons, much the same way that the phototubes you're using probably are, but they're run at a lower amplification within the photomultiplier tube, so that the output signals are smaller, and there's less wear and tear inside the TMT from this very high rate of noise photons. So you get with one telescope, you get an image of the shower in the camera plane. With multiple telescopes, you basically get two different views of the shower as stereo views, and you can use that then to reconstruct the image, where exactly what direction in the sky the gamma ray came from. So if you take multiple images from different telescopes and overlay them in the same camera plane and look at the axis, where the axis of those images intersect, this corresponds to the position of the direction of the gamma ray on the sky. And similarly, by looking at where these images intersect on the ground, if you extrapolate them from the telescope, you can determine where the gamma ray how far from the telescope the gamma ray would have landed. So from the orientation of these images in the camera, you can reconstruct the shower direction and the shower position on the ground. From the amount of light you record in the image, you get the gamma ray energy. So the more energetic the gamma ray, the more particles are produced in the atmosphere, and the more Cherenkov radiation that those particles produce. And so you get the energy that way. And then from the shape of the showers, you can distinguish gamma ray showers from proton showers. So these are now simulations and these are simulations for a future instrument called the Cherenkov telescope array. That will have a much larger camera than the Veritas cameras. One of the telescopes will have a camera here with about 2,000 photomultiplier tubes, but there's another telescope design that we're working on where there's actually 10,000 pixels in the camera and with very fine resolution. And these are images of a 1 TeV gamma ray shower in both of these cameras, and you can reconstruct the ellipse. You can also sort of see the bright section of the ellipse near the top of the shower, and then the tail as the particles get absorbed in the atmosphere. And these are two images of proton showers, where particularly in this higher resolution camera, you can actually sort of see individual rings, which are the rings of individual high-energy particles, most likely muons, that were produced in this proton shower. And so these two showers look very different in what the images look like in the camera, and this allows us to differentiate gamma rays from the background protons. So moving now to some of the science that we do with these instruments, one of the major outstanding questions in high-energy astrophysics is, where we know that the Earth is being bombarded with cosmic rays. Where are these cosmic rays coming from? And for a long time, there's been a hypothesis that they're coming from that they're being accelerated in the shocks of supernovas, and we're just now getting to the point where we have enough evidence to really see that this is likely the case. This is one of the first images in very high energy gamma rays of a supernova remnant. So this is a supernova remnant in the southern hemisphere, and the color scale here is actually the image in gamma rays that was constructed from the Hess experiment. The Hess is a very similar instrument to Veritas, but it's in the southern hemisphere and looking at the southern sky. And by being able to basically not only see gamma rays from the supernova remnant, but basically to resolve some of its structure, has been an important part of trying to understand what particles are being accelerated in the supernova remnants and testing models of cosmic ray acceleration there.
So the x-axis, those are degrees and minutes?
Oh, right. So the x and y-axis, so the x-axis here is in right ascension, which is measured in hours and minutes. It's an celestial analog to longitude. And this axis here is declination, which is the celestial analog to latitude. So that you can think of this like longitude and latitude on the sky. And this is the color scale here is the intensity of gamma rays that are being seen from a particular direction.
So that image is about a half a degree.
Yeah, this image is right. So this is half a degree here. So the diameter of the image is close to a degree.
Okay, so that would be twice the size of the moon in the sky. That's pretty good resolution for the equipment, the instrument. The moon is half a degree. Right.
So another result, recent result, and this is a result from Veritas that was actually led by a postdoc here at Santa Cruz, was to discover pulse very high energies from the crab. So the crab pulsar has been known as other for a long time at many wavelengths in radio and X-ray and optical. It's a neutron star that's rotating very quickly, and there's basically a beam like a lighthouse that's sweeping by our field of view every 33 nanoseconds. 33 milliseconds. And what's done here is we take the gamma rays that we see from this with Veritas, and we use the information that's measured in the radio in terms of the phase and period of the pulsar spinning, and we basically say for each photon where in the phase of that rotation was the photon detected by Veritas, and we actually see then peaks where the gamma rays come at preferred times with respect to the rotation of the pulsar. So this is an indication that there are very high energy gamma rays that are part of this lighthouse beam from the crab. And this was not expected theoretically. The model that predicted gamma rays that were seen by Fermi did not expect that this emission would extend up to the Veritas energy range above 100 GeV. So this has been a puzzle that theorists are now trying to understand in terms of what's the mechanism in this rapidly rotating pulsar that's able to produce gamma rays with such high energy while keeping them sort of in a tightly focused beam of the lighthouse. It's been known for over 20 years that there are unpulsed gamma rays from the crab system, so that this pulsar is powering high energy particles that do produce very high energy gamma rays, but those processes are sort of over much larger time scales where the gamma rays just come in a steady stream. They're not associated with the lighthouse at the very center that's spinning very rapidly. So this was a very interesting result to see that there are gamma rays being produced so close to the pulsar and associated with its spin. So another system that we looked at is a binary system. This is this has two objects that are in orbit around one another, and from other observations, the parameters of the orbit are known, and what we see is that they're gamma rays that are emitted from this object, but only at certain points around the orbit. And this provides some clues to what sort of the gamma ray emission mechanisms are. And one of the nice things about these systems is that because there's an orbit, there's basically a repeating. The objects come back, and so you have a chance to you have a system that varies, but it varies in a predictable way. This is a very interesting system then for studying how high energy gamma rays are produced, because if you see them here, and then you can wait until the system comes back and get another pass to look at them again.
Is this orbital period like years, or?
This orbital period is about a month. It was actually one of the things that made these measurements difficult is the orbital period was very similar to the period of the orbital period of the moon. And during the full moon, the sky is bright enough that it's difficult to take observations. So sometimes when it gets in phase where all of the time of the month when you want to take the observations on this is the same as the time that the moon is up. But then, the periods don't quite match up, so the following year, things will be a little bit out of phase again.
The phi values, or those gamma ray emission things?
These phi values are phased around the orbit. So that the orbit is defined in such a way that actually I'm not sure quite how it scales, but somehow they go from 0 to 1 as you go around the orbit, but it's not, it's somewhat of an odd scale, because you see this is 0.1, but then 0.1 over here is a much smaller distance. So I don't remember exactly how this phi is defined, but it's a parameter that parameterizes where you are around the orbit. In this particular system, there are a couple of different hypotheses for how it could work. One is that it's the so-called microquasar, where there's a compact object here, either a black hole or a neutron star, that has material from the companion star that is feeding an accretion disk, and so the material is being pulled off this companion, going into an accretion disk that's spiraling into the star. And in systems like this, there are very often then jets of particles along the rotation axis, and so that these relativistic jets may be the source of the gamma rays. And in fact, you see sort of the eyeball here, sort of you're looking at the line of sight might be looking sort of along these jets. Another idea is that there's a pulsar. That the compact object is a pulsar, and there's a massive star that has a large stellar wind, and that the pulsar is interacting with the stellar wind to produce shocks in which particles are accelerated and the gamma rays are being produced. So this is the so-called binary pulsar scenario, and it's still open for debate which of these which type of system this particular object is. But by getting more and more detailed observations, we can try to test these two models and ultimately figure it out. So moving to these objects I've been talking about are all within our own galaxy. The Crab pulsar and this binary system and the supernova remnant are all galactic objects. On the scale of stars or a binary system at the scale of a couple of stars. But as we move to extragalactic objects, we start to look at things at the level of galaxies. So there's a radio galaxy called M87, which is a gamma ray source, and this is a number of different images of this source. So this is a large-scale, comparatively large-scale image. And then if you zoom in to the central region with the instruments that have very high resolution, Chandra and X-rays, and the Hubble Space the Hubble Space Telescope in optical and radio observations, you can see that at the center there's sort of a jet here that's shooting out from the center. And in fact, there's even some structure in this jet with different, these so-called knots of bright, intense emission along the jet. And then if you zoom in on this region even closer with very long baseline interferometry in radio, you can resolve even the central portion of the jet and sort of see the base of the jet as it starts out. And so this is sort of typical of an active galaxy that has a supermassive black hole at the very center that weighs perhaps something like 10 to the 6 to 10 to the 9 solar masses. So a very massive black hole in the center with material that's feeding onto that black hole and powering jets of particles that are being emitted along the rotation axis. So this was a microquasar, which is sort of at the stellar scale. But these objects at the galactic scale, the ones where this jet is oriented along our line of sight are an example of quasars, which very bright. The term quasar comes from quasi-stellar object. These were objects that were extragalactic, but they appeared nearly point-like. So they were quasi-stellar from the sense of being nearly point-like objects, but they were so far away they had to be tremendously powerful. And now what we believe is that these objects are, we're basically looking down the jet axis of this jets that are being produced in the central region of the galaxy. And so with Veritas, we've looked for, we can compare data. So these are now looking at as a function of time of the emission of from various regions and in various wavelengths. So this is radio data of the emission, and this is the emission from the center, from the nucleus. The nucleus is this region right here at the very start of the jet, and in comparison, there's also emission from one of the knots, one of the bright spots, which was brighter and then faded, and the nucleus here got brighter around the same time that we saw an outburst of gamma rays from this object with Veritas. And so we took this as an indication that the gamma rays were coming from the very central nucleus at the very base of the jet, rather than from one of the bright knots along the jet. And so this was an indication that the very high energy particles were being accelerated within about 100 Schwarzschild radii of the black hole at the very base of the jet. And this is one of the best determinations so far of the location of particle acceleration in an active galaxy. Are we aiming for me to go for about an hour, or?
We're good for whatever you need.
Okay. So let me talk about one other type of measurement we can do for an extragalactic object. And so this is Markarian 501 is an active galaxy, which is in many ways is similar to M87, but in the case of M87, we're sort of seeing these jets. We're seeing these jets sort of from the side. But with Markarian 501, we believe that we're actually looking right down the barrel of the jet. So these jets are pointed right at us, and here are again, these are so-called light curves. These are looking at the rate of gamma rays. So the y-axis is the rate of gamma rays, and the x-axis is time. What was seen here was a very rapid change in the rate of gamma rays with times of the flux changing by a factor of 2 in a period of about 2 minutes. So this is one of the most rapid variations that's been seen from from a gamma ray source. And what this does is it allows us to say, again, to say something about the emission region. So if you imagine you have some region that's of size D that's producing gamma rays, and in a sort of an instantaneous flash that produces gamma rays over this whole region, and so photons that are emitted from point 1, point 2, point 3 at the same time. But as an observer, we see them arrive at different times because the photon that's emitted from the backside, if we're over here, the photon that's emitted from the backside basically has to propagate an additional distance d, and the photon that's emitted from the limb, sort of from the side of the object, has to propagate an extra distance d over 2. So if this region is transparent, then it means that we would see, when we see all of these photons, it means that the arrival times will be spread over a time that's of order the size of the region divided by the speed of light. If the region is opaque, so that we don't see the gamma rays that are emitted from the back, and we only see the gamma rays that are sort of emitted from this front surface, then the gamma rays are still spread out over a time that's about half of about the radius of the object, the size of the emission region divided by the speed of light. And so, if we see gamma rays, the gamma ray flux changing on a scale of 2 minutes, it means that the size of the emission region has to be very small, and related to these constraints here on the if it's a transparent region, it would be sort of 2 minutes would correspond times the speed of light would give you roughly the size of the emission region.
How can you make the assumption they're emitted at the same time?
Well,
are they coming from some event at the center?
So if they're not emitted at the same time, that's going to stretch out the time even longer. So the way that you get the shortest possible pulse from this object is if all these photons are emitted at exactly the same time. And that gives you then if the photons are emitted at different times, then you need an even smaller region.